Thank you.
I am really glad that you guys have all stuck around to the end of this 2-week workshop. I've included not a whole lot of code, not a lot of math, but lots of pretty animations. So hopefully your brain fatigue can muscle through the next about half hour or so. So I wanted to share this project that we've been working on with a couple of partners, some folks from NCAR and some people from Hewlett Packard Enterprise, about joining machine learning techniques with our traditional kind of like high performance computing, scientific numerical simulation codes. So just kind of to start off with, right? I mean, like there is this huge push to kind of say we want to be able to do machine learning and enhance our numerical simulations. You know, we get this from our managers, we get this from everybody else. Machine learning is, you know, the biggest thing in the world. Everybody wants to try to figure out how we can improve our applications using it. One of the problems, though, right, is that they come at the question kind of from two very different approaches. Machine learning and data science, give me enough data, I'll solve all your problems. Numericists like me, we're like, just give me the equations and enough Taylor expansions and I'll solve all your problems. These are two fundamentally different approaches, where one is kind of relying on deriving fundamental equations, and the other one is kind of using more ad hoc heuristic kind of things, but large amounts of valid data to basically solve the problem. So in order to actually solve this problem about how we use machine learning and high performance computing in traditional numerical codes, we first have to reconcile some philosophical differences, right? And really the best way, and I think one of the reasons why our collaboration really was so successful, is because we got together some domain scientists, some data scientists, and computer scientists, and really just spent like a lot of time just getting to the same page, explaining to each other what the questions were, you know, how the approaches might be different, how the approaches might be the same. And it really was this interesting exercise in having very intelligent people who are experts in the domain, not having a single clue what somebody else was talking about. So there's definitely a little bit of language translation, in addition to kind of just like knowledge diffusion that had to happen before we could actually make a lot of progress. And then also combining these two requires reconciling some very technical challenges as well, right? So machine learning is probably like, you know, the most common language used for machine learning is probably Python, right? A lot of the examples that we've seen today are based on the Python implementations of like TensorFlow or Keras or ONCs or anything like that. There are some C++ backends, but if you're like me and you live in a domain where Fortran is the lingua franca, the question is, how do you hook up? How could you possibly hook up to something like a C++ code? So that's just a major hurdle. Like, forget figuring out the right problem, you know, to the right scientific problem to ask. This is one of the just technical hurdles that we have to overcome. And then the secondary question is, how can we do this machine learning at scale when we have heterogeneous architectures? And what I'm talking about, these are platforms that have CPUs and GPUs and codes which might be CPU dominated or GPU dominated. So these are all kind of challenges that we had to work through. And we have one example. I think our collaboration is one example of us kind of overcoming a lot of these things that I hope others might be able to kind of get some inspiration by. So my domain is in climate modeling. I'm an oceanographer, and unlike most people's conception of what an oceanographer is, I do not in fact study whales. I think about the physics of the ocean and then how we solve the equations of motion on a sphere. You know, it's very fluid dynamics oriented. So a climate model is not just physics, but it also incorporates chemistry and biology. And so, like, you know, the one of the big reports that came out was this assessment report 6, which gives the summary of climate science, the current state of climate science. And part of the chapter, especially the one projecting what the changes are going to be in 21st century, relies very heavily on these climate models. You know, so we're modeling basically all the components of the climate system, which includes the land, the ocean, the atmosphere, sea ice, land ice sheets. Some models are also doing icebergs. So these are very, very complicated models that are all being coupled together to kind of give us this emergent state. And one thing that distinguishes climate models from a weather forecast, oftentimes we'll use the same kind of component models. And by that, I mean, like, it's the same land model, it's the same ocean model, atmosphere model, but climate models are always freely running. We're not trying, you know, especially when we're projecting out into the future, we have nothing to constrain those future predictions by. So just a real quick sidestep to just talk about where climate modeling fits in the HPC, the high performance computing kind of perspective. I'm just going to give an example of the Canadian contribution to this coupled model into comparison project on which this climate report was based on. So our atmospheric, our ocean and ice models are about 100 kilometers. The atmosphere and the land are about 300-kilometer resolution. And then we discretize in the temporal with that about a 1 hour time step in the ocean and 15 minutes in the atmosphere. And just to give you an example of what one climate change experiment might look like, we do one simulation, which we call the pre-industrial control and integrate that for about 2,000 simulated years. And then we would do another 150-year experiment for the historical period, and then another 85 years for the 21st century projections, right, from 2015 to the 2100. I mean, one of the big things that we also need to do is many ensemble members, where these are all perturbed slightly differently to account for the internal variability of the climate. So in total, CANISM-5, which is the Canadian climate model, we did 300,000 years of simulation. We have stored 40 petabytes worth of data on tape. We're serving 500 terabytes of data to be used by all sorts of downstream users, and probably spent about 150 million CPU hours to do all these climate simulations. And one thing to really note, CANISM-5 is actually one of the lowest resolution models, and there's significant biases when we're running such coarse models. To resolve the largest scale of turbulence in the ocean, we actually would need a model that was about 1,000 times more expensive. So there's this real kind of balance between running a model that's small enough to be run for these thousands of years and capturing the necessary physics. And especially as we go more into the future climate modeling, we know, generally speaking, that the science of climate change is settled. And so now the demands on us are more for regional projections so that we can do climate adaptation and also climate mitigation. So by what we mean with that is like with more extreme events, what areas need to plan for that? What kind of precipitation might a region have that changes over the 21st century? And so in order to do that, we actually will need some higher resolution models, because especially on these kind of more regional questions, like for example, what's happening in New Mexico or what's happening in the Midwest or the West Coast of Canada, we just need higher resolution models. So one of the really important things that is determined by the resolution of the model is turbulence, right? So turbulence is just this incredibly challenging problem. It pops up all over in fluid dynamics. And just to give you an idea of how much of a problem this is, I'm showing the output from a resolution from a model that was about 50 times finer than what we typically run our climate models in. And so what you can see here, all these little structures, all these little circles and like long filaments, this is turbulence, right? This is the effect of turbulence. And one of these white squares, that's about a typical size of a box in the model, right? Like that's one grid cell of the model. And when you're modeling something like this, you actually need kind of 4 of those to roughly get to actually resolve a physical feature. So if you can imagine, right, like, these 4 boxes basically represent what one grid cell in our big climate models actually are. So if we're not resolving this, we can't get it. So first of all, our images aren't as pretty, but turbulence is also super important to the actual fluid dynamics of the problem, right? It is a first order effect on modeling the ocean circulation. So stepping down into equation land a little bit, what this actually means, if we write down some of the equations, the governing equations for the circulation of the ocean, what this basically boils down to is that there are these terms, which we call kind of these like eddying terms, which are these prime terms. And then there are these mean flow or like kind of resolved flows variables that are indicated with this overbar. So like this U bar is a term that would be resolved by the model. And these U prime terms are things that the turbulence is doing that in these coarse resolution models we're not able to directly represent. So if you just zeroed out these terms, which is what a coarse resolution model is doing because it can't resolve those terms, you're missing a fundamental part of the equation. So yeah, thank you, Chris. And so parameterizations, where parameterizations of turbulence come in, is that we're trying to capture these eddy terms, but using the resolved terms, right? So we're trying to use these large scale quantities to estimate what these terms actually are. So one of the approaches that the community is taking is kind of this pure data science approach. So we replace these terms wholesale with a trained model, right? You have a super high resolution model like the one that I was showing in the previous slide, and you just train a machine learning model to kind of directly inject the terms into the equations as you're solving them numerically. The big problem with that is that we don't know necessarily how to actually constrain those terms, right? Like these machine learning models, you can build some physical constraints into them, but it's really difficult to actually make sure they're doing things like conserving momentum, conserving energy. And so it's been used with kind of varying success, but I would argue that most of the literature in the climate science domain, these are the machine learning parameterizations work in kind of idealized settings, but they don't necessarily scale well to these really large realistic simulations. So the approach that we took here is to say, let's combine the data science approach, but let's also rely on some understanding of the physics. So we have a lot of existing turbulence theory to give the functional form of what these eddying terms might look like. So, we have something that looks like f of u bar b bar, and we have derived that from kind of fundamental physics. But what we're going to do with the machine learning side of it is to predict the strength of that, right? So the particular parameterization that we're targeting is one of the most famous ones, quote unquote, in oceanography, which is a Gent-McWilliams parameterization. So what the Gent-McWilliams parameterization actually does is that it actually ends up smoothing horizontal density gradients using a specific diffusivity. And so a horizontal density gradient, like the ocean, is the density of the ocean is largely determined by temperature and salt. And there are fronts in the ocean where there are huge horizontal gradients in that, which lead to density gradients. And so what Gent-McWilliams does is it mimics the process of what eddies do, which is to basically smooth out those density gradients. The strength of that at any given time is given by a diffusivity or a coefficient. The original ones, and even in current climate models, oftentimes that coefficient is constant in space and time. More leading edge kind of research is showing how we can actually calculate that, get a spatially temporarily varying coefficient if we can also estimate the eddy kinetic energy associated with this turbulence. The current bleeding edge prognostic equations for doing that, though, for calculating this eddy kinetic energy, either completely omit some terms or very poorly approximate some very key terms in it. So this was one of the reasons why we actually chose to say, let's replace this prognostic equation with a machine learning model, right, with a neural network, because hey, we can't do any worse. And you know what? We can also have some constraints on the eddy kinetic energy. So even if the machine learning model gives us, a prediction that's completely out of bounds, we at least know how to control for it without directly affecting our very sensitive dynamic numerics. So our approach was to replace this kind of prognostic equation that calculates or that tries to estimate eddy kinetic energy with the neural network. We generated training data using a 10-kilometer resolution ocean model. So that's enough to kind of capture the larger scale of turbulence. That's shown on the right here. So you can kind of see those same eddying structures, especially like on the east coast of the United States. That's the Gulf Stream, and there are these rings that get shut off, and similarly down there. So this is the turbulence of the ocean. And then so when we do that, we can then calculate both of those eddying terms and the mean terms from that equation that I showed before, from the model that's resolving both of those, and then train a machine learning model by doing that kind of averaging that I was talking about before to separate out the eddy scales and the mean resolved flow scales. So we have a model that's basically able to ingest those mean fields and predict the eddy kinetic energy. Then we can hypothetically do that at a coarser resolution model and predict the eddy kinetic energy grid cell by grid cell. And then that eddy kinetic energy that's predicted is then transformed in the model using known equations to generate this coefficient. So we're not wholesale replacing the functional form of this parameterization. We're just using the machine learning to predict the strength of it. And so just a quick kind of thing to show what these features that we're using to train the model on look like. So we have data that we took from the 10th degree model. We averaged it down in 2x2 boxes, 6x6, 3x3 boxes, all the way to 10x10. And you can see that the distributions of these features kind of change depending on how much coarsening you're doing. And the reason why we did that was essentially we want to be able to come up with a machine learning model that's general enough to be used at multiple scales, depending on multiple coarsenings of the resolution of the model. So this mimics what the Reynolds averaging does in those equations and what the targeted low-res simulations are able to resolve. And so just on the right-hand side, this is just like a typical plot of the validation aspect of it. On the top panel is what the actual eddy kinetic energy is as we calculated it from the high-resolution model. And then the bottom panel is what the eddy kinetic is what the neural network actually predicted. So as you can see, the large scale features are very similar. One of the big things to note is that the bottom one actually looks sharper, quote unquote, than the truth. And that's because, again, right, the machine learning, we're not incorporating any spatial information in the training of this model, and we're doing everything grid point by grid point. So the neural network is trying to give the absolute best prediction of eddy kinetic energy grid cell by grid cell. And so that leads to a natural kind of sharpening of the predictions. I'm going to just kind of blow through this real quick. If anybody's really curious about the NeurIX, I'm happy to talk about it, about this particular model. I just want to say that one of the other reasons why we really want to target this particular simulation to improve is because it was a model that was used in this big intercomparison project. It's been used for regional modeling. We use it for coupled operational weather predictions. We use it to try to simulate the past. And we also use it for fundamental kind of climate and oceanography research. So it's got a lot of use cases, and being able to improve this model would be really phenomenal. So we ended up doing this, and I'll explain the technical part of it first, but I just want to show what this looks like when we ran this coarser resolution model, this 25-kilometer model, as opposed to the 10-kilometer model, where we sent data out from the model, had the neural network predict eddy kinetic energy, and then give that back to the model. And this inference was done every 3-hour time step of the model and was done, again, grid cell by grid cell. So again, the animation I'm about to show is the coarse resolution model that has eddy kinetic energy predicted in it from the neural network. So as you can see, as this model is evolving in time, right, there is the generation of these kind of smaller scale features that look very turbulent-like. This was done. It gives us the turbulence in the right places. Off the east coast of the United States, there's an elevated amount. In the Southern Ocean, there's elevated turbulence. And so this is really phenomenal to us. Just for a comparison of what this looks like compared to the previous bleeding edge approach, is called the mesoscale eddy kinetic energy. That's shown on the right. So the prognostic equation that we're replacing would give us a pattern that looks something like this, right? Where there's almost no energy anywhere in the ocean, except for maybe a couple places in the Southern Ocean. Whereas in using this like smart sim neural network approach, we actually get turbulence in the correct places. It looks right, it's about the straight strength. And if you take just averages going across latitude bands, this is the eddy kinetic energy that we would get. So the previous state of the art was this line down here. And as you can see, it vastly underestimates what the eddy kinetic energy should be. This middle line right here is what the quote unquote true eddy kinetic energy should be, as represented by this much higher resolution model. And then this is what the prediction of eddy kinetic energy is, given this neural network approach. And one thing I really want to stress is that we don't actually care that much about the fact that it's over predicting near the equator, this little bump here. What we really care about is that it's matching the predictions for eddy kinetic energy in this region, kind of the 20 degree to 40 degree north kind of place, because that's where we know there is a real real effects of turbulence in the ocean. We did this in an ensemble of simulations as well. We ran 11,000 cores, 910 cores per member. We had 16 nodes doing these inferences with V100s. We integrated for full 20 years. There was no crash instabilities. It ended up being about 1.5 million core hours and 1 trillion inferences over the span of about a week. And it was only about 6% slower to run this neural network than this previous prognostic equation. And just for comparison, that 6% is completely acceptable to us because running a 10th degree model, a 10-kilometer model, would be 15 times slower. So we're happy to take a 6% performance degradation to get much better, but still be able to run the model at a coarser resolution. So we were pretty pleased by that. So that was kind of that's the application side of it. And then I just want to draw back a little bit to explain kind of the software solution that we came up to actually do this and that is available for all similar models. So we call it SmartSim. And essentially what it's doing is that it's coordinating ensembles of simulations, a database, and other components. And so what I mean by this database is that this is a Redis AI distributed database with GPUs. And MOM6 is on the left-hand side, so that's the ocean model. And that has MPI, ranks, and each of them have a client that is able to communicate with this database that's existing on GPU nodes. So the MOM6 MPI ranks are on CPU-only nodes, and the database itself is running on nodes with GPUs in them. And so every time step, what's actually happening is that MOM6 is sending the subdomain. Every rank is sending the subdomain, the features on every subdomain, sending it to the network, or sending it to the database. The database is then queuing up an inference of this ResNet model of this to predict the eddy kinetic energy, and then sending the data back to MOM6. This Redis AI distributed database, because it's based on Redis, its data is stored in a key value data store. It supports all the major machine learning packages. So we were using TensorFlow, but it also supports Keras, scikit-learn, et cetera. And the database is scalable to the size of the problem. So we use 16 nodes. You could scale it. We've scaled it up to 64 nodes, and it works just fine. And one of the key components of this is that the Fortran-based model, in this case MOM6, is only interacting with a Fortran client. It doesn't have to know anything about Python, doesn't know anything to know about C++, but yet you can actually connect Python code, C code, C++ code, because they can all share data within this one centralized database. This is what the code kind of looks like in MOM6. It's pretty easy to instrument. I think we did this in about 50 lines of code in the MOM6 model, where it's essentially you just have to initialize the client that will communicate with this database, set identifiers, load the machine learning model into the database, and then every time step on every MPI rank, you're putting a tensor, you're saying, run the model, give me a prediction, and then you're retrieving a tensor from the database. And so all the inference is done on the remote database, and that means that you don't have to continually update some Fortran implementation of a neural network. You can just rely on TensorFlow that's running on this Redis AI database. And this also means that the MOM6 nodes don't need a local accelerator. This is one of the big problems, is that most of these climate codes are CPU-based codes. And so it would be very inefficient if every node that we're using to run that model on also had a GPU accelerator, because we'd maybe be using the GPU 1% of the time, which is not an efficient use of resources. And lastly, I just want to kind of just zoom out a little bit, because we originally designed SmartSim to solve this problem of the convergence of machine learning and traditional high-performance computing numerical codes. But when we started actually really playing around with it, we realized that we can actually enable a lot of new computing ecosystems by just having this common database where data is being stored between various parts of it. So one thing that we had demonstrated before is that we can actually communicate with the Fortran-based MOM6 using a Jupyter notebook, right? So we can send data from MOM6. We can have a Jupyter notebook that has a Python client that can communicate with that database. And we can get data that's being sent from MOM6 to be passed back into our Jupyter notebook to do analysis or visualization without ever having to go to disk to output any data to disk. The other thing that we can do is that because we can send data into this database, and then MOM6 can retrieve data from a database, we can actually do some direct computational steering. So for example, what I mean by that is that I could tell, if I instrumented mom6 correctly, I could tell mom6 to stop, or like ask if it should stop after a day. And I could then just send it a completely new ocean state via that I've loaded up in Jupyter, and then stored in the database. And then mom6's internal state would have completely changed. The other really nice thing about this is because these clients are written in Python, C, C++, we can connect different packages that are written in different languages together, and they can share just that fundamental data, right? Which is just what is the internal, what are some of the prognostic variables in this model, and do something with them. So one of the big things that people like to use on this large scale client model output is particle tracking. So that's essentially dumping a whole bunch of virtual particles in the ocean and then getting the flow field from the model to move those particles around and just see where they go. The other things that we can do with it, we can do real-time data monitoring. You could do some rapid code prototyping. So for example, if I had a new subroutine for some new numerics that I wanted to just send back and forth to mom6, I might be able to write that in Python first, and then figure out how to translate that into kind of fundamental Fortran later. So it's a lot of these new kind of very interesting, I think, new kind of paradigm for high performance computing, where we can not only just kind of like run these simulation models and just kind of let them go, but we can directly interact with them or have kind of follow on needs for them, like this particle tracking or data monitoring that we might need to do. So I hope that was a clear enough overview of how we combine kind of data science and these classical physics approaches to improve a global scale realistic ocean climate simulation. And just as a reminder, we placed a key prognostic equation in the model that has a first order effect on the simulation accuracy with a neural network. Then we demonstrate scale by doing this on an ensemble of ocean runs on a heterogeneous cluster with high CPU and GPU utilization. So just for context, I think we hit something like, well, we were at 100% CPU utilization and something like 90%, 95% GPU utilization. So instead of just, which is what all systems administrators want to see, is that high heterogeneous utilization. I explained a little bit about SmartSim as this lightweight solution for creating kind of these multilingual computing ecosystems, and that's in a scalable framework. And then we've got some ongoing projects that we're doing. SmartSim source code is completely open source. It's available at github.com/crealabs. We're doing some actual climate scale length integrations with SmartSim right now. We're also thinking about how to incorporate machine learning into a different Earth system model, the one that's being developed at NCAR, so we can do kind of high resolution hurricane tracking and intelligent model sampling. So we're not necessarily outputting the full global 3D fields at high resolution, but we can just selectively sample basically where the hurricanes actually are. We're incorporating SmartSim into NEMO and mom6 and a variety of other computational models as well. So if you want any additional information, feel free to contact me. That's my email address there, andrew.shaw@canada.ca. There's also a Slack channel for SmartSim itself that if you have interest, you can just ping any one of us on there and talk about whether your application is useful or not. And then finally, there is a paper on the archive that describes kind of the technical setup and some metrics of this SmartSim simulation that an ensemble of ocean runs that we did for this paper. And so with that, I am happy to close out and take any questions that you might have.
Thank you. Do you have the Slack open? There's at least one question in Slack.
Yeah, I can open up the Slack. So yeah, so we don't actually connect Fortran. So the question is, how did you connect Fortran with Python, F2Py? So we did not actually connect Fortran with Python, and we've tried doing that in the past, and F2Py is great, except when it doesn't really work. And there's all sorts of Fortran structures fundamental Fortran structures that don't actually work with F2Py. So what we're actually doing is we're sidestepping the problem, right? So we're calling this Fortran client, which then calls a C client which then communicates with the database. So all this, like the Redis API is actually written in C++ and C. And so by relying on Fortran C interop, which is much easier to deal with than Python and Fortran interop, we're able to kind of connect this Fortran model with the database itself. So thank you for that question.